Hello everyone, our presenter today is a visitor from the University of St. Andrews, Dr. Samiur Rahman, who got his master in Sweden and his PhD at UCL London. And ever since then, he has been working with the Millimetre Wave Group at University of St. Andrews. Welcome.
Thank you, everyone. First of all, thank you to taking your time this Monday morning to attend this presentation, and also lots of thanks to Graham Brooker for arranging this. Very kind of him. So I am Samiur Rahman. I work as a research fellow with the Millimetre Wave Group at the University of St. Andrews, and today basically I'm going to give an overview of the radar research we do at St. Andrews. So the Millimetre Wave Group is basically the Millimetre Radar Group is basically part of the radar, and also electron paramagnetic resonance spectroscopy. So basically, we do both. I work on the radar side. The radar side is basically run by Dr. Duncan Robertson. I work with him. So he established this group about 20 years ago. So our team is essentially in two parts. We do environmental remote sensing and also, of course, it's radar. So there's of course going to be lots of security applications. And we built lots of demonstrator radars, mostly FMCW and mostly coherent, because we got a lot of we gather Doppler information corresponding to the applications that we have. We have over the last couple of decades, we have built quite a few radars. I think right now we have about 13 radars in the lab, ranging from 24 gigahertz all the way up to 340, built for various applications. We don't do any electronic scanning like phase arrays. It's all mechanically scanned, real aperture, real time beam imaging. And so yeah, for security applications, so we work on lots of projects like crowd control, then concealed object detection in various security parameters, and also drone detection and classification. That's a project that I've been working on for the last 6-7 years. And also we have done quite a lot of remote sensing. My colleague has been involved in volcanology and glaciology, terrain mapping for the last couple of decades. So that was actually the first project that Duncan started back in our part of the video. And volcanic ash was sort of like the extension of that project that started a few years back. Then we also built a cloud profiling radar that we have up on the roof. And then also currently I've been working on sensing autonomous vessel sensing, but not automotive car. It's for marine autonomy, and also lots of millimeter wave, so with lots of short range characterization of various materials. And so in the radar part right now, we have one principal research fellow, which is Duncan, the head of the group, 3 research fellows, including me, and currently we have 3 PhD students. So it's a very small group, but the university is small itself. It only consists of 10,000 students, but the university is actually 600 years old. So and it's located in the east coast of Scotland. So quite a nice place, but slightly remote. And yeah, so we got various funding from different funding bodies in the UK and also internationally. So for instance, like the concealed object detection was funded by a large Horizon 2020 project, and also we worked with US Army Research Lab for various security related application projects as well. Just a very brief overview about what we do with millimeter wave. So millimeter wave kind of sits in the sweet spot between microwave and infrared and optical, where you get sort of like the halfway house of both. So here you can see just a very basic example. To the right is of course the optical image, and then you can see that millimeter wave can have better obscurance, which can be useful for various, short range security and also environmental monitoring applications. So that's the advantage we use. So you can have small form factor devices with millimeter wave and also sub-millimeter wave. So you can have for a given gain and everything, you can have smaller size antennas that can be more compact, that you can move things around a little better, and you can have narrow beam, and also because it's millimeter wave, so you can have larger fractional bandwidth that you can use for higher resolution. And because as I mentioned before, that it's longer than infrared, so you get that obscurance that you. So for example, here the bottom right, you can see that in optical image that's kind of on the top of the mountain in Montserrat, gets covered by the cloud, but your millimeter wave kind of penetrates through, which sometimes might not be the case with infrared. So the group kind of does everything from scratch. So traditionally, it's an instrumentation group. As I said, the group does both radar and spectroscopy. So the group started with building spectrometers, like W-band millimeter wave spectrometers, and so we do the design, we do the system design, we do the CAD modeling. We have a workshop where in the workshop you can basically assemble the whole radar system, and then we do the lab test, then we do field deployment for various applications and so on. So we are kind of jack of all trades but master of none in that regard. So now basically getting into various projects that we've been working on. So the drone one that I've been working on, I think these days we are all quite aware of what sort of threats drone pose. So this is a slide that I had from 2016 or 15, where we were trying to convince people in various organizations in the UK, government-related, to basically say what sort of threat look for this. It's not always that people are using drone for nefarious purpose. It's also that people are using drone in a way that inadvertently poses a security threat. So, and the threat is also sort of kind of twofold in a sense that you get threats from military side, which is usually rural areas, very long range, but you also get threat in an urban area where there are lots of things blocking your view, blocking your line of sight. So the technology is actually still not fully developed, simply because the threats are quite wide range, and also the drones are evolving. It's a very, very fast-paced market, and you can just buy a commercial drone and you can just mod it. I mean, you guys are working in robotics, you guys know this stuff way more than I do. So, for instance, like one of the main detection method is just RF sensing. So if you have a commercially available DJI drone, and it's almost like the way we detect a song in Shazam. So you just sniff for the digital signature. But if someone is actually trying to use it in a different way, then they can very easily bypass that. And so the way we do is, of course, we are a radar group, so we focus on the radar sensor used for drone detection. And the tool that we use is called microdoppler. So it is sort of an extension of your bulk Doppler. This is just to give an example. So if a person is moving, so that's a bulk Doppler, but the motion within the object. So for a human being, it will be legs and arms moving. So that creates a Doppler signature in the sideband. So here you can see the yellow, the middle, the dorsal motion, but you can also see the Doppler signature from the arms and flames. So same thing happens with drones. So specifically for rotary wing drones, so you get a distinct microdoppler signature stemming from the propeller blades. And the idea is that you can use that information to detect that it's a drone or not, because you can't just use a built-in navigation, built-in airport radar that is purpose-built to detect an aeroplane, which usually has a huge radar cross-section for flexibility. So you can just flexibility. So you can just use that information. So for drone, it's low altitude, comparatively slow moving. So you need a different sort of technology for that, not just translate directly. So, well, the advantage of radar is this is sort of a selling point of radar that we always say that it's a all weather condition, which is actually not true for millimeter wave in most cases. But well, we have to start with positives first. So yeah, and as I mentioned that yeah, RF sensor can sometimes have these drawbacks in real-time scenario. And yeah, radar can of course, give you a very good localization. And because we are using microdoppler information, so you go high up the frequency, your Doppler frequency increases, the Doppler sensitivity increases, you can use that information for better classification. So the research started in 2015. I joined in 2016, but there was a student project started in 2015. That's sort of what started this whole area of research for us. And so in the beginning, when we started, what we did was that at that time, there wasn't that much data available for drones at these high frequencies. So we just gathered a few radars, and actually the 24 gigahertz radar we built for specific to this project, and we just gathered lots of data for target characterization. Basically, before building any purpose-built system, we wanted to know what sort of system design we need, what sort of big budget we would need for this application. So we did radar cross-section RCS analysis, which is just measuring the reflectivity of the specific targets of the radar. We did huge amount of microdoppler analysis, and also we did lots of work on algorithm development for classification using your basic signal processing. At first, I started with that, and then it was the time when AI kind of popped up into the scene, and we thought that even though we have absolutely no clue what AI does, but we should get on board as well, and we try to learn machine learning and deep learning and all this stuff, and applying those techniques for drone detection. And we're an academic group, so we have to publish papers to keep us afloat. So along that time, we have published quite a bit in conferences and journals. So for drone detection, the main confuser is of course BERT, because the RCS that I was talking about, the reflectivity, is more or less the same or similar, as you can see from here. And we use different frequencies, lower like 24, higher 94. And even if you go lower frequencies, S band or X band to 10 gig, the RCS is quite similar. So you can't just use that information for drone detection the way you can just use that information for aeroplane detection. So so because of that overlap, we used, as I mentioned before, microdoppler analysis, and then we apply lots of machine learning techniques, neural network techniques, and we get very good results. But you have to keep in mind that it is very narrow data set. So we gathered some data in the lab, not in the lab. I mean, drones are flying outside, and we get say 1,000 data points, and we analyze that. We get really good results, but this is no way any guarantee that if you deploy it in a different environment with lots of more data, eventually the performance will match up. So we always keep that in mind, that what's actually going to happen in reality. So and the thing is that it's not, there is also no guarantee that whatever technique you are using is actually generalized. It may be that it's going to work for your radar system, because for instance, like convolutional neural network, that was built for optical images, right? Our radar, the microdoppler signature that we use, spectrogram that we use, we try to treat it as optical image, but at the end of the day, it's not. So depending on your signal processing, depending on your Fourier transform window, your spectrogram is going to change massively. Just visually, it's going to change massively. So whatever your CNN is learning with one sort of signal processing data, it's going to learn an entirely different thing if you process it in a different way, how you're thresholding your noise floor and everything. So it becomes very specific to your data that you're feeding for training. So you have to keep that in mind as well. But at least it's a starting point that technique works in some ways. So as you can see here an example, so the vertical lines are red flash, so that's basically when a propeller blade is rotating and it has the maximum view with respect to the radial beam of the radar, so you get a nice flash. And once you have your Doppler sampling rate is fast enough, because these propeller blades are rotating really fast, like 100 to 200 hertz rate. So you can unambiguously sample, and you can even see that depending on the shape of the propeller blade, you can get different signatures, which also implies that in an ideal scenario, you can even distinguish between different types of rotary wing drones just by analyzing the propeller blade signatures. And then on the bottom right, you see wing beat frequencies. So that's the vertical lines there are actually coming from the wing beats of the bird. And the rate, the rotation rate is going to be different. So then you use various classification techniques based on signal processing or modern neural network and so on, and you try to find the difference between these two. And this is just an example, and as I was saying, so that was like the very, very first attempt that we made. So using different types of Doppler features here, we were using 3 or 4 years to see plots of 2 features. Just I think it's 7 or 8 data points. It's very, and you see a very clear discrimination. So that kind of gives us hope that that might be a good direction to go. And the idea was that it was commercial. So we'll build a prototype radar, which eventually we can commercialize, because at that time there was a gap in the market for low-cost portable drone detection radar. So the ones that were available by the companies, and they were selling it for close to £500,000, £1 million, and they were really big, and for the military applications, so they were covering like 10-20 kilometers because they were mostly using it open rural areas back in the Middle East. So our market was that, can you make something that will just cost 50K, and some sports organizer can basically buy it for their Olympic event or so on. So the first one we built was a 77 gig, and the reason for using 77 is simply because there was a transceiver chip available at 77 gig for stemming from the automotive car industry. And it was a very good radar. It was very low phase noise, which you need because you need purity in Doppler, because that's the domain that you are using for your target classification. But the point is that you go high on the frequency and your range coverage drops significantly. So it was just covering, like 300 odd meters or so. So the stakeholders basically say, well, it's really nice, but I want to look further away. 300 meters is not good enough for us. So we and also the other thing is that if it rains, 77 GHz radar is absolutely no use for you in terms of in terms of drone detection, which we knew beforehand. But at that time, most of the commercially available drones were not massively IP rated. So our argument was that if it's raining outside, no one's going to fly a drone. But that argument went out of the window quite a while ago. So we had to come down the frequency, again 24 gigahertz, another frequency band for automotive car. So we used a very cheap analog devices evaluation board. So that's basically the evaluation board we used to build our first 24 gigahertz radar for the data collection phase that I mentioned before. So we basically extended that technology beyond that. I mean, technology extension is the bit of a fancy word. But what we basically did is we use some frequency dividers and so on. We use the reference clock to make everything coherent, and we incorporated an amplifier to basically so that it shouts louder and so on. And then what we found out is that this is a range Doppler plot. So vertical axis is your distance, and then x-axis you have your Doppler signature. So whenever there is a bright target present, so you get your, because of the poor phase noise performance, your noise floor rises up, which gets cancelled into your Doppler, and you can see all these signals, all these high level elevated signals. That's basically messing up all your classification algorithm entirely. So it became entirely useless. Because that's the domain we are using for our classification algorithm. So then we made the second version of the 24 gigahertz radar. The difference is that the chirp generation is using a different technology, direct digital synthesizer, DDS based, which has a very low phase noise performance. That basically means that you have better spectral purity. Well, it's low down the frequency compared to 77, so your range coverage is has improved. Now it's 1,000-meter detection, and that the baseline here is the standard DJI Phantom 3. So it's 1,000-meter detection for DJI Phantom 3. It will be even more if you're using a larger drone like DJI S900 hexacopter or so on, and it will be smaller if you're using a small like DJI Spark or Mavic. And currently, we are basically trying to quantify our classification algorithm. So what basically we did that we deployed, gather a bunch of data, and the classification is done in real time, as I can show here. So on the left is a PPI plot, and you can see, so this is a radar here. These are the trees. These streaks that you see, that's a hardware artifact coming from bright targets. We still think this is mainly some mixer saturation that we have got, but it doesn't affect the Doppler, so it's not actually phase noise. So, but we still haven't got to the bottom of it, which we want to. And the right one is the classification algorithm. So what the algorithm does, it just picks up the drone, and then it just points to the drone. Everything else should be blanked out.
So can you see the drone on your PPI plot? Is it visible?
Yeah, it should be.
Oh, that one over there. Okay.
But from a PPI, you wouldn't know whether it's a drone or not. So then you plug this whole data, especially in the Doppler domain. This is just your raw amplitude, of course. So you analyze it in the Doppler domain in real time, and then it basically picks out which one is the drone according to the Doppler features. And then, so it's not doing any sort of MTI processing or anything. It's not doing any sort of conventional detect, track, and identify. It's just directly getting raw data, doing the Doppler processing, and saying there's a drone or not. And the main challenge is that in some data you will have birds. So what you need to do is that find out that your algorithm is actually just picking up the drone and not the bird. So that's how you kind of tweak the threshold. And so far, what we have done is we have done sort of manually, in a sense that I have like 4 or 5 thresholds corresponding to different features. And what I do, like running the data set and seeing that, oh, okay, probably I should it doesn't see the drone up there. That probably relax my threshold a little bit. But that's a very unscientific way to go. So basically what we are doing right now is trying to generate rock curves with different thresholds and so on. So one of our colleagues is working on this right now. And so once we have that documentation, because you need that documentation, basically when you're doing the commercial exploration, because people will ask what sort of performance matrix you have. And as I mentioned, so we did some project with US Army Research Labs. This is just an example of one of those. So here, what they wanted to know is that can you use radar for any sort of biochemical weapon detection, which is being sprayed using a drone. And we bought this crop spray drone from China, and but we couldn't buy any biochemical weapons simply because we were not allowed to. So we just used water. But the idea is that hopefully the reflectivity would be the same. And this idea basically stemmed from when we were doing any sort of testing with our millimeter wave radars prior for years. So whenever we'll be doing any sort of radar test, we'll find out that in the Doppler domain, we get see signatures, even though we don't have any idea it's raining outside. Then one of our colleagues was actually standing outside to confirm that it started to drizzle very slightly. I mean, we view both theoretically and from experimentally that our radars can actually pick out even the small drizzles very easy. And so basically we did some measurements, we did some modeling first, that what should be the volume reflectivity coming from these droplets. And then, so the blue line is at 94 gig. That's the solid blue line is the theoretical one from the modeling. And the dotted blue line is the experimental data. So sort of matches with the model. I mean, we were not expecting any sort of better match. We kind of thought that this 3 or 4 techniques should be okay, because we were having a very hard time always having things in the board side where the drone was flying and so on. But 24 gig, you can see that there is a theoretical curve, but there is no measured curve simply because we couldn't see anything at 24 gig. And that basically confirmed sort of our modeling that it was kind of okay, because the big budget that we had, we were expecting that the 24 gig should not be seeing anything. But our modded 24 gig drone detection radar that we have, which has a large dual amplifier, that actually sees rain as well. So again, the argument that it's an all-weather radar, it's not always true. The project that I've been working on right now is on autonomous boats. So basically, it's sort of a kind of a analogous to autonomous car that you guys are very well tuned with. The main difference is that for autonomous car, the roads are static, the buildings are static, so you can do sort of background subtraction in some way if you know, which is not always the case if you know what your surroundings are. But the reference for a marine autonomy is, of course, it's very dynamic. Your sea is very dynamic. The sea, lake, river, it's dynamic. So you need to know the statistical properties of that. So you can't just do this background subtraction. So, and most of the marine radars are quite low band compared to what we work on, which means that around mostly about X-band. X-band is sort of the traditional marine radar operating frequency. And most of them, not all, but quite a lot of marine radars are just not coherent anyway. So they don't use any Doppler information whatsoever. So if you want, so the market that we are going for is sort of small to medium-sized marine vehicles, because if you want to turn our oil rig then you actually need to see quite a few kilometers away. And these high frequency radars are just not going to cut out for that. So the frequency range of frequency of our interest is about 100 to 300 gigahertz. The idea is that you have very good resolution, so you can map your surrounding, close surroundings quite well. You can have very good Doppler information. You can have all these fancy neural network techniques or machine learning techniques that you can make some sort of smart decisions very quickly. So that's sort of the idea. But it will be again, sort of low cost portable thing. It's not going to be used for a massive ship. Or it can be, the other idea is that it can work in conjunction. So you use your low frequency radars for your overall surroundings, then you can actually use the high frequency ones for short range, more localized, to gather more localized information. And this is quite of a large project. It's about a £1.5 million project funding that we got, project in conjunction with Birmingham University Radar. So they are sort of like currently I would say the largest radar group in terms of number of personnel in the UK. It used to be UCL, but nowadays it's Birmingham University. So they have quite a lot of resources in terms of manpower in our.
So Samiur, so you talk about autonomy on these boats. Are you actually using this for collision avoidance? Or are you using it to actually look at waypoints and actually navigate a specific trajectory? What are you?
Mostly for collision avoidance to begin with.
Okay.
But it's also basically the idea is autonomous navigation in the end. But of course, we're going to do sensor fusion for that.
Yeah.
It's not just radar. Radar will be one of the sensors for that. But it's not only for like research vehicles. It's for any commercial vehicles or anything.
So, for example, you could put these onto all the boats in the Thames, and then you could actually then have them drive autonomously.
That is basically the idealistic vision.
Okay.
Yeah. That's how you can use that. So that's why, but in order to do that, you need a solution that is cheaper, right? So, for instance, like for this project, okay, I'm coming back to that. Next slide. So the main drawback here is that at these high frequencies, we have absolutely, almost no data whatsoever that how the sea looks like at these high frequencies. We have no clue. So at first, you need to know that. So this project, even if it's a large project, is not the end goal of this project. Is actually not to build a demonstrator radar like the one we did with our drone project. This project entirely focuses on focus on the phenomenology study, essentially, that how the sea looks like at these frequencies. And then eventually the idea is that you can use this information afterwards. So the idea of this project was going all over the UK, collect data of sea clutter, collect data of marine targets like whales, sea mammals, and so on. So it was the whole shebang. And then the COVID started, so we were all sitting at home, and we were modeling and trying to convince us that it's going somewhere. But eventually, COVID ended, so we started our data collection, and so we used 6 radar 3. So the underlying ones are the ones that we are using: 24, 94, 220 should get it, 207. That's the frequency. So 24 and 94 gig radar that we already had from our previous projects. So one of my colleagues with a PhD, finishing his PhD. So one of the works that he did in his PhD was build this 270 gigahertz radar from scratch. So he did a fantastic job. It's a really thing. But as Graham was saying before, that what sort of radar we use and why. That 270 radar gives you very good data, but it is massively expensive. So you can't, with the current technology, there is no way that you can use that for a commercial. No fisherman is going to buy a 270 gigahertz radar. because the LNA itself costs 10 grand. So forget about the rest of the technology. It's quite, but the technology is not there. But even though I mentioned the frequency of interest is sort of 100 gigahertz plus, but we use these lower frequencies, 24, 79, simply to basically bridge the gap between the existing data, because we are doing phenomenology studies, so we are actually the model of sea clutter is all done with empirical data anyways to begin with. So you need this limited, and nothing is available beyond X band. So what we thought that having data points up to 10 gigahertz, then all of a sudden jumping to 150, we might not know whether the correlation is actually justified or not. So we thought that we could also gather data at these lower frequencies so that we can see the trend and we can make sense that whatever the modeling that we are doing is actually correct or not. And we did multiple trials so far in the UK, went to the district, and St. Andrews is it's in the East Coast, so we have a beach right next to our office. So we gathered some data there as well. So I'll show some examples. So this is basically a 94 gigahertz data, range, time, intensity plots. It's basically steering mode. This is a steering mode measurement. So radar is just pointing to the shore. So these are the waves that's going away with respect to the radar, hitting the shore, breaking waves. So these are the signal return coming from the breaking waves. And so that's sort of the starting point of analyzing the data. And then, of course, we do frequency comparison. So this is the same data at three different frequencies. The 24 gigahertz has slightly coarser range resolution. That's simply the hardware limitation. So it doesn't go beyond 60 centimeter. It doesn't go finer than 60 centimeter range resolution. And then you see 94 gigahertz on the top right, and then on the bottom is 107 gig. The difference that you see between 94 and 107 is that the 94 gigahertz getting, so all these diagonal lines are basically you getting reflection back from the crest of the wave that's coming towards you. So it was basically the radars were mounted on the shore. So it's basically the waves that come in towards you. So you are getting reflection from that, and it's actually just time history. So you just get the diagonal line kind of comes from the top to bottom here. So comes closer to the edge. But you see that the 207 gig just picks out the brightest ones most of the time. So there are two things happening here. One is, of course, 94 gigahertz radar is far more sensitive compared to the 207. So if you it's harder to maintain the same beam gain when you're going higher frequency. So it just has more RFQs compared to the 270 radar that we have. But whether it also has the frequency dependency or not, we are still not sure. So this is the data that we're trying to analyze that. It's very, so it basically picks out the spikes. So where you can see at 24 gig, it is the reflection is more distributed. And this is what you also see at 10 gigahertz data, that the reflection that you see is more distributed. But when you go high up the frequency, then your returns become more spiky. And that agrees with the very few papers that were available did some sea clutter measurement at this high frequency. They observed the same thing, that it was a more spiky return. And so these two are sort of the similar. Like you can see that that's quite of a bright red. It's a strong return that you can see at 207, but you don't see the other ones as well. Scanning. Pick out a target in front of you. But it becomes difficult when when the clutter. So this is a very low sea state here. This is like, it was a very calm day. But when your sea state increases, then this whole scanning plot is going to light up, and then the whole thing is going to be quite difficult for you. One thing, of course, that we found difficult for the field trials is that in order to do this phenomenology study that I'm talking about, you need data at various sea states, starting from low sea state to high sea state. All the data that we are gathering so far is mostly low sea state, because we are taking our radars outside, and you can see they're open electronics and everything. And to protect them, we just have this gazebo. So we are actually looking for nice weather. So when but the problem with nice weather is that even though it's good to take a radar outside, sometimes the thing that you're measuring, the sea surface, or in this case, lake surface, is absolutely flat as a pancake. So you are actually not getting that much out of it. But on the other hand, if it's really, really windy, then we live in the UK, so it's almost guaranteed that it's also raining on the outside. So we were supposed to go to a trial just a couple of weeks ago, and again the wind was quite good, and then it was absolutely hosing down, so we couldn't go. So, and you need that data because all the modeling is done with empirical data, so you can't just extrapolate from low sea state data. That can't happen. We actually do data. So they're still looking for the perfect sweet spot where it's windy like hell, but it's absolutely sunny sky. And also along with Flutter, so you need various targets. So we put various targets on the water as well. And that's how we use our PhD students. This is one of our PhD students who was told to swim. It's a calm day. So, and he's from Finland. So this is absolutely yeah. So then you can see the picture. It's a spectrogram plot. He's zooming away, so you can sort of a video motion from his arms kind of getting translated into the spectrogram. And the idea is that this Doppler signature will be different from the Doppler signature coming from the sea clutter. And hence we need these high frequency radars to get this better Doppler sensitivity, because it's quite hard. I mean, unless you make a very sophisticated radar, it's unlikely that you get this kind of Doppler information from a 2 GHz radar. So that's why that's sort of the argument that we made. That even though you are using range coverage, but you are getting this sort of potential robust classification performance. And we also made other main targets like sea lions, because as Graham was pointing out what sort of thing navigation we want to do. So one thing would be, if you see a marine, if you see a sea or something, at least it should be able to pick that out. What is your, so here the radar sensor, what we care about right now is how much can pick it out. What is your decision-making process, whether you will maneuver around it or not? That is sort of a high-level decision-making that depends on what sort of boat it is, what sort of things it's navigating. But what we want to know right now is how much things we can pick out. Can you actually say that this is just a pallet, so it doesn't matter if it's a pallet, or is it something like a whale or something that you actually can maneuver or not? So, and again, in terms of literature, there is very little available at frequencies. So we went to Sea Mammal Research Unit and basically collect data of sea lion for the very first time. So we did amplitude statistics analysis, we did Doppler analysis, we published papers, and pretended that it was all very sciencey thing. But you can see our PhD student getting absolutely excited. So, but it was all good, because this is sort of like very first glance of radar data at these high frequencies of these targets.
So you're going to come out here and do dolphin measurements in, in Sydney, are you?
Oh, well, yeah. That's another excuse to another excuse to come to Sydney. Yeah, exactly. I mean, we have a field colony in Scotland, so we were supposed to at some point, hopefully before the project ends, go there to collect data. But yeah, it all depends on which season you are going and so on, and also lots of ethical approvals. Even though our radars are very, very low powered, but still you can't just turn up. I mean, you can do it for, you can go to our beach next to the office and do some sea surface measurements. But if you're going to a seal colony, slightly more paperwork that you need to do. So now some other applications. So one of the projects that one of our PhD students have been working on is glacier mapping. So we went to Swiss Alps in 2019, and also in 2021 or 2022 we went to Svalbard, basically north of Norway, to use one of the. So this radar was originally built for the volcanic ash measurement that I showed before at Montserrat in West Indies. So they took that radar and it does sort of your azimuth elevation raster map, so you can basically create a digital elevation map. And because it's millimeter wave, so you can get high resolution, and then the idea that you can tie this with other sensor data like LiDAR, and you can do lots of exciting analysis with it. And again, no data available mostly. I mean, there is data available, but not that much at the high frequencies for glacial mapping. And this is another project that's been ongoing right now. So Mark Bell, the PhD student, so he was a final year project student, worked with me, and now he's doing a PhD. It's a industrial funded project funded by Leonardo. So basically, the idea is that in the UK, we actually don't have that much information, reliable information in terms of the infrastructure surrounding us. So the idea is that can we actually put a radar on a crane, which is sort of a low-cost solution, and you kind of do SAR, interferometric SAR imaging, or whatever, these kind of techniques. Basically, get information of your surroundings. So this is what he's doing. And right now, the project is sort of, is working on the basics, which is still frequency independent, and Leonardo don't work with high frequency radars, mostly solid expand. So, but the lowest radar we have is 24 gig, so he's working with 24 gig radar right now. We'll collect some data, so try to make a jig, basically like a rail radar outside our lab. So that will be the starting point. So, and then the other project that kind of went on during the COVID time was volcanic ash characterization. And that is basically an indoor measurement. So you kind of drop ashes, and you have various sensors, you have radars, you have cameras, LiDARs, and everything. You get the reflectivity, and you measure various statistical properties to know how they behave, what sort of reflectivity they have, and so on. And the chamber is at University of Lancaster, and my colleague, Dr. Dan McFarland, he built these triple frequency radars. So you get frequency variations, in the frequencies are 10 gigahertz, 35 gigahertz, and 94 gigahertz. And they are all pointing in the same direction. So you get data of the same volume, volumetric cube, but at 3 different frequencies. So then you can do all sorts of property analysis. And they did some measurements at Lancaster. This was actually done less than a year ago. You can see from the radar point of view, ash is falling, and you can see the reflectivity and then the idea, lots of amplitude characteristics. analysis.
So Samiur, why should we care about this radar, this ash?
Mainly because if you want to use radar sensor for to basically map survey volcanoes, so you need to know that what sort of properties, radar properties they have, and of course the starting point is doing it in the lab. So that was the project. The theoretical idea was developed by people at I think University of Reading, but they didn't have radar expertise. So that's how they collaborated with Duncan and with hardware here. But the signal processing analysis is I think going to be done by both I think Reading and Lancaster. And now another security application, people screening at various premises like airports or any sort of stadiums and so on. And again, in that case, you need to use very high frequency radar for high resolution, and that was sort of Duncan did this work, started this work a few years back, and I think they used 220 gigahertz radar. So they do this either 220 or 340, I forget. So they do this sort of elevation mapping, and you can see this actually took, so this was all post-processor. This was not real time. It took quite a while to do that, but that was sort of a proof of concept begin with, that you can actually get this kind of this kind of performance. And then they got this EU funding to create airport security scanning radar at operating at 340 gigahertz, and that was a massive project that went on for 4 years with various other partners all over the Europe. And so this was a this project they took it to Finland to so where the VTT were the other project partners, where they'll be using other sensors as well. And then this was sort of the real-time proximity. You can see the shearing. I think the shearing was, I'm not 100% sure, it was coming from some sort of processing delay or something. So it wasn't actually real, but it was sort of a proof of concept. And then what happened was technology sort of moved on to flat panel antennas. I don't know whether you guys have seen that at the airport. Road insurers were making these systems where you can just stand like this. So this kind of pan mirror based rotating. Most of the airports are not massively interested in it, but it was a very nice. It was probably, I would say, in terms of hardware, that was the most complicated radar hardware, or one of the most complicated radar hardware, if not the most, that was built by our group, which is right now, I think it's just sitting there in Finland. But according to Horizon 2020 evaluation board, it was a massively successful project. So the idea is for some other application, it might be used, but not for airport security, so because of the technology, so in a different direction. So that's sort of the flavor I hope I could give you guys a little bit of what we do. So that's our website underneath. So if you want to learn more about specific projects, you can just go there and see that for slightly detailed information. And many thanks again for your time.
Yes. Any questions?
So thanks for the talk. When you're measuring sea state, when you're measuring returns off the sea, are there tools that try to simulate that, that try to guess what answer you should get?
It's the other way around in a sense that whatever the tools are available, they are all based on previous empirical data. So this is sort of a advantage and disadvantage we have in a sense that whatever data we get, because there is no data available at say 24 or 94, whatever data we get, we can just claim that this is for real, which I'm going to do a few days later as well at the conference. But the idea is that if we see that the reflectivity has some sort of trend that matches with previous data, which again, I mean, even the equation, the modeling, the equation is only that depending on which model you use, they are valid to different frequencies. So you will, if you use it depends on what model you use. If you use one model, it's valid to up to 10 gigahertz. If you use another model, it's valid to 1 to 35. Then there is a gap. Then it's valid to 94 to 100 and something. And simply again because what sort of empirical data was used, and also not all the models are valid for all C states. So it's, I mean, we use the existing tools, of course, to get some sense out of it, but it's really difficult to objectively verify that, you know, if that makes sense, that what we're seeing is correct. That's why I was saying that when I showed that 94 gig and 207 gig data, where 94 gig is picking up almost everything, and 207 only picks up the brightest ones. I mean, of course, we know from our hardware that 94 gig sees more, simply because it has more overall RF power. But what is the frequency response? How the electromagnetic wave is behaving at these two different frequencies, and how much that contributes the return? That is actually very hard to determine, and that is a part of the project, that you have that data and you basically compare and contrast that the existing model, you upgrade the existing model, upgrade the equation of the existing model, and see if that makes sense. Then you can then that upgraded equation actually fits all the data points starting from 2 gigahertz up to 94 or 207.
So I get that data-driven simulation is dominating there. Is physics-based simulation is hopeless?
It is way too complicated. I mean, the data-driven simulation also uses the physical properties, of course, but it is. I mean, and it's been all the low frequency data that I've been talking about. They have been done a long time ago, and mostly by American military, back in the 60s and 70s. So there has been a large gap. So I mean, maybe they have more information, but that's not public. But in whatever that's available in the literature, it's all low frequency empirical based. And as I mentioned, that there are different models. The reason for different models is that the way you model the C states, the way you model the C structure, that also varied in terms of global location. So, you know, what we measured in the North Sea, the UK, is different from the model that was present somewhere else. So it is quite and mathematically it's quite challenging. So there one of the researchers named Simon Watts, who did all the pioneer work, and the other person is Rosenberg here in Australia. So they did pioneer work, all sorts of modeling, and yeah. So and they published a paper a few years back. What are the challenges? And one of the challenges they mentioned is basically this, because it is heavily data-driven modeling, which is not always ideal, especially, you know, but it is how the C is so dynamic in that sense that it's hard to get away from.
Any other questions?
It's Samiur. So you've been doing fairly a broad range of different frequency measurements of your C states. Why don't you have an X-band radar there anyway? Because I mean, everybody else has done measurements at X-band.
So the the plan is, that the commercial partners or the industry partners we have in this project, like, Rayleigh or NAVTEC.
Yeah.
So they have X-band radars already. So the idea is that when we go to the field trials, they tag along with us.
Okay, so you bring your high frequency radars and they bring their low frequency radars. Okay. Yeah.
X-band radars. So far, because these kind of field trials with 2 universities, and depending on weather, depending on people's availability, it becomes so hard to actually basically arrange one, that so far we haven't been able to time sync with one of them. And, and they also require specific location in a way that they just can't come to St. Andrews. It has to be somewhere near their area where we have to go to. But the idea is that before the project, we want to collect some X-band data as well. And one of the work that has been done in this project is that they have huge amount of X-band data, these companies, but they don't have any sort of analysis expertise. So they want to do it, but that doesn't work that well because it's a different data from what we are
yours. Yeah.
So the ideal scenario is to get an X-band radar along with us as well. And this is also, as I mentioned, that hopefully before the project ends, we can go to a trial where we have one of these companies joining us along with their radars.
So Samiur will be here for most of the afternoon. So if anybody else has other questions or would like just to meet the guy, please feel free to. He'll be in my office or tagging around, so we can basically chat to him. I think it's probably time for us to have a bit of lunch, don't you think?
Yeah. Now if online have questions, no response. Okay.
Okay. All right. Thanks.